Hello all, welcome to the new lecture of partial differential equations. We were discussing about the one-dimensional wave equation. In the last lectures, we were discussing about the Cauchy problem for the one-dimensional wave equation. We have proved that it has a solution. There exists a solution which is given by the D'Alembert's formula, and also by a proposition we have proved the uniqueness. Now we will discuss about the condition for well-posedness of the Cauchy problem for the non-homogeneous one-dimensional wave equation. The theorem is, first fix t capital T greater than 0, the time t, the Cauchy problem given by equations 1 and 2, that is utt minus c square into uxx equal to f of xt, where minus infinity less than x less than infinity and t greater than 0, u of x0 equal to f of x, ut at x0 equal to g of x, where minus infinity less than x less than infinity. In the domain minus infinity less than x less than infinity and 0 less than or equal to t less than or equal to capital T is well posed for f comma fx is in C of R2 small f. The external force F and its partial derivative with respect to x is a function of C of R2, and small f is a function of C2R, and G is a function in C1 of R. Okay. So we need to prove the well-posedness. A Cauchy problem. We know that a Cauchy problem or a PDE is said to be well-posed if it has the three things. That is, the problem should have a solution. There exists a solution, and the solution must be unique, and it should be stable. So in this case, for the non-homogeneous case, we have already proved the existence by the D'Alembert's formula for the Cauchy problem of non-homogeneous one-dimensional wave equation. And by a proposition, we also proved the uniqueness. If there is a solution, then it must be unique. That we have already proved by a proposition. Okay, you can watch the videos for that. So in order to prove the well-posedness, here we need to prove only the stability of the solution. Okay, so it remains to prove the stability. That means we need to show that for small changes in the initial conditions and the external force capital F give rise to a small change in the solution. That is meant by the stability of the solution. So if there is a change in the initial conditions and in the external force, it must give rise to, or it must bring comparatively a small change in the solution. Or we need to prove that mathematically. Suppose for I equal to 1 and 2, let ui be the solution for the Cauchy problem with the corresponding functions capital Fi, that means capital F1 and F2 as the external force, and the initial conditions as small fi and gi. That means there are two problems. First one with the equation with utt minus c square into uxx equal to f1 of xt with the initial conditions u at x0. u1 at x0 is f of x, ut at x0 is g1 of x. And another problem with a capital F2 and initial conditions ux0 as F2 of x, ut at x0 as g2 of x. So if there are such problems with the solutions as u1 and u2, then and if there is only a small change in the external force, that means the external force, the change in the external force modulus of f1 of xt minus f2 of xt is less than delta, and in the initial conditions with respect to the small change in the initial conditions, that means mod f1 of x minus f2 of x is less than delta, and mod g1 of x minus g2 of x is less than delta for all x belong to capital R and 0 less than or equal to t less than or equal to capital T. Then we need to prove that according to the small conditions, for any epsilon greater than 0, there is a delta such that mod of u1 of x minus u2 of xt, u1 of xt minus u2 of xt is less than epsilon. So that we need to prove. So first of all, we consider the difference of the two solutions, modulus of u1 of xt minus u2 of xt. So by the D'Alembert's formula, we have the solution u1 of xt is by definition it is equal to modulus of 1 by 2 into f1 of x plus ct plus f1 of x minus ct. Note that u1 is a solution for the Cauchy problem with the external force capital F1 and initial data small f1 and small g1. Okay, so the solution is 1 by 2 into f1 of x plus ct plus f1 of x minus ct plus 1 by 2c integral x minus ct to x plus ct g1 of s ds plus 1 by 2c double integral over delta capital F1 of theta tau d theta d tau minus 1 by 2 into in bracket f2 of x plus ct plus f2 of x minus ct plus 1 by 2c integral x minus ct to x plus ct g2 of s ds plus 1 by 2c double integral f2 of theta tau d theta d tau. That this is given by u1 of xt minus u2 of xt. Now this is under the modulus sign, and we know that mod of a plus b is of the form is less than or equal to mod a plus mod b. Okay, so before that, first of all, we combine like the functions with the same values. That means f1 at the same points x plus et. So from the first one, 1 by 2 into f1 of x plus ct, and there is minus 1 by 2 into f2 of x plus ct from u2. So we combine like that. So 1 by 2 into, we can write it as 1 by 2 into f1 of x plus ct minus f2 of x plus ct. Now consider the same for x minus ct. So from the first u1, 1 by 2 into f1 of x minus ct is there. Then plus we combine the terms under the integral sign from x minus et to x plus et. So it is from u1 we have 1 by 2c integral x minus et to x plus et g1 of s minus g2 of s from u2 of xt into ds. Then plus 1 by 2c double integral over the characteristic triangle delta f1 of theta tau minus f2 of theta tau d theta d tau. Now we apply the triangle inequality for these four terms. So this will be less than or equal to 1 by 2 into mod of f1 of x plus ct minus f2 of x plus ct plus 1 by 2 into mod of f1 of x minus ct plus f2 of x minus ct plus 1 by 2c modulus of integral. So that will be again less than or equal to modulus of integral function. This will be less than or equal to integral of the modulus function. So we have it is 1 by 2c integral x minus ct to x plus ct modulus of g1 of s minus g2 of s ds plus 1 by 2c double integral over the characteristic triangle delta modulus of f1 of theta minus theta tau minus f2 of theta tau d theta d tau, and number it as the inequality as inequality 3. Now we will reduce all these terms. We have taken mod of f1 minus f2 as less than delta, and also mod f1 at the point x plus ct and also at x minus ct. So the first two terms will be 1 by 2 into delta plus 1 by 2 into delta, and the second integral, under the integral there is mod g1 of s minus g2 of s, that is also less than delta, and we can calculate the integral. So for that, integral x minus ct to x plus ct mod of g1 of s minus g2 of s ds is strictly less than integral x minus ct to x plus ct. Instead of this difference, it is less than delta that we have already taken. So this is delta into ds, that is delta into s from x minus ct to x plus ct. So applying the limits, we have delta into x plus ct minus x minus ct. So it will be 2 ct into delta. Now we have to calculate the double integral. Double integral over the characteristic triangle delta mod f1 of theta tau minus f2 of theta tau d theta d tau will be less than double integral over delta mod f1 minus f2 is again strictly less than delta. So it is delta into d theta d tau. Now we have to integrate d theta and d tau. The integral of d tau will d theta will be theta, and then we have to apply the limits, and we just remember or remember that this is the characteristic triangle in the theta tau plane, and this point, this is the point xt, and this line, it is the theta from theta is equal to x minus c into t minus tau, and this line is theta equal to x plus ct, x plus c into t minus tau, and we are and the integration theta varies from x minus c into t minus tau to x plus c into t minus tau, and tau varies from x equal to x tau varies from 0 to t. Okay, so this is delta into integral tau from 0 to t and integral theta from x minus c into t minus tau to x plus c into t minus tau d theta d tau, which is again less than delta into integral d theta will be theta, and tau varies from 0 to t. Theta from the limits x minus c into t minus tau to x plus c into t minus tau d tau. Now substituting that values, the both the limits we have, this is equal to x and x will get cancelled. It will be 2c into t minus tau d tau. Now again integrating with respect to tau, we have it is 2c delta into t tau minus tau square by 2 within the limits 0 to t. Now applying the limits we have and simplifying, we will get it as c t square into delta. So the double integral is less than c t square delta, and the integral of g1 mod g1 minus g2 is less than 2 ct into delta. Now substituting all these in the inequality 3, we have mod of u1 of xt minus u2 of xt is less than first one 1 by 2 into mod f1 of x plus ct minus f2 of x plus ct. This is 1 by 2 into delta. This is also 1 by 2 into delta, and this one we have calculated as 1 by 2c into 2ct delta, I think. Yeah, 2ct into delta, and the double integral is less than ct square delta. Substituting all this in the third inequality, we will obtain it as delta plus, which is less than delta plus delta t plus delta t square by 2. Taking delta outside, this is delta into 1 plus t square by 2. And also given that 0 is less than t less than or equal to capital T, which is a fixed one. Fixed number. So mod u1 minus u2 is less than delta into 1 plus capital T plus t square by 2. And this will be less than epsilon if we choose delta as less than epsilon by 1 plus t square by 2. That means for a given epsilon greater than 0, we choose delta as a number which is less than epsilon by 1 plus t square by 2 for a fixed capital T. Then for all x belongs to R and 0 less than or equal to T less than capital T, the difference is less than epsilon, or mod u1 minus u2 will be less than epsilon. So according to the small changes in the initial function or initial data and in the external force, there is only a small change in the solution also. That means this proves the stability of the solution. Therefore, the Cauchy problem is well posed. Okay, thank you. Thank you all.